All right, so here I am with um, Process Dynamics and Controls, Homework 1, Part A. I'll be starting out in this little, this kind of whiteboard here. Actually, let's start by reading the problem. So we have a cylindrical tank with a uniform cross-section and a drain hole at the bottom. And we have water flowing at a constant rate, and liquid level has reached a steady state. And then we are going to derive the differential equation describing this height of the liquid in the tank as it responds to an increase in flow. So we have our tank, and we have some height h, right? And we have a flow going in. That'll be called Q in. I'll just call it QI. It's a little easier to write. And we have a drain hole called QO for out. Right. So now, what we want to do is look at how this changes with time. And to do that, we're going to analyze the Bernoulli equation. So that is way too big. So I'm just going to take the sum, and I think here, let's make a paragraph. It will look a little nicer. So Bernoulli's equation says that sum of all, it's essentially an energy balance. Well, it is an energy balance, not just essentially. Now, I'm going to do this on a per mass basis, so I'm not going to be adding mass in here. It would all just cancel out. But we have the sum of all potential energy plus the sum of all kinetic energy plus our pressure over density. And if we add all of those going in and coming out, they will equal 0. All right. So for this pressure over rho, our pressure on the top of the tank is 1 atmosphere, and the pressure at the outlet is also 1 atmosphere, and our densities are of course the same, so that it's canceled out. Now we have GH plus V squared over 2. I'm actually going to, well, yeah, we'll make gravity negative. So negative 9.81 is our gravity term. Although you could also use 9.81 and a negative height. Either way will work. So here, this gravity term, potential energy term, we just have gravity times the height of the tank. And then for kinetic energy, the top of the tank is wide, so we are just going to assume there's no motion there. So our V squared over 2 becomes V out squared over 2. And this equals 0. Now, what I want to do is, it'll look nicer if I just say this GH is negative, and we'll call gravity 9.81, so that we can add it to the other side. So then it becomes GH. Let me make this a little smaller. GH equals V squared over 2. Right, that's just adding GH to both sides. Now we can multiply by 2 on each side. And then solving for velocity, we get that V naught equals the square root of 2 GH. All right. So now we have our velocity coming out of the tank. And to convert that to our volumetric flow rate out of the tank, we can just multiplied by the cross-sectional area. So times A out, and this becomes, instead of velocity, it becomes volumetric flow rate. Now, the reason I solve for this volumetric flow rate is because this height change, right, if we take dH dt, is going to be dependent on the flow coming into the tank minus the flow going out of the tank. And to go from volumetric to height, we can multiply by our cross-sectional area. Right, now plugging this equation in up here, we get that our dH dt equals Q in minus A out times the square root of 2GH all over the cross-sectional area. This is our differential equation. Now to move on to that initial value, right? We know it's at steady state, so we know dH dt is 0. So we could just set this this right-hand side to 0. So 0 equals Q in minus, I'm bad at those guys. Let me try to make that a little better. Q in minus A out over, or sorry, multiplied by square root of 2GH. Immediately we can take out this cross-sectional area term because we just multiply by both sides, and 0 times any number is 0. Now we want to solve for our height. So we can add the area, cross-sectional area going out times square root of 2GH to both sides. And that will give us that it is equal to Q in. Now we can divide by A out. And what I will actually do is separate 2G from height, because height is our variable of focus here. And then that just shows that we can also divide by square root of 2G and cancel that out. So now, squaring both sides, it won't let me draw here. Okay, I guess I did. Click that again. Now we can square both sides. We get that our height at the initial steady state is the flow going in over cross-sectional area going out times the square root of 2G. Oh, I did not mean to go through the equation. All right, so now we have these two equations here. dH dt equals Q in minus area cross-sectional area out times the square root of 2GH all over cross-sectional area of the tank. And our initial height, I will label that as, we'll call it H naught. H naught equals flow going in over the cross-sectional area going out times the square root of 2G. And now I'll be moving into Python and first Excel, then Python to use these differential equations. All right, so here I am in Excel. I'm going to get started by inputting my variables. So our initial flow going in is 0.1 meters per meters squared per second. Sorry, meters cubed per second. Yeah, I don't know why my arrow keys aren't working today, but they are not. So I'll have to click each box. It's a little bit slower, but that'll be all right. our flow after our time starts is going to be 0.15 meters cubed per second. Our initial, or sorry, not our initial, our cross-sectional area is 1 meter squared, and our cross-sectional area going out is 0.2 meters squared. We also need to make a time step, so I'm just going to make that small 0.005 seconds, and we need gravity, so 9.81 meters per second squared. And then I'm going to go through and name all of these, so Q name that. Just using this little name tag up here, it's the top left. And then calculating our initial height. This is just straight from the equations we just derived. So we have our initial flow going in over our cross-sectional area going out times the square root of 2 times g. And this is all squared. Oh, my variables didn't work. I didn't hit enter on them, that's fine. I always forget that part. You have to hit enter, you can't just click up. So that should be all of them. There's our initial height. Now I'm gonna make our counter here. So we'll start at 0, and if we go to this menu here, we can make a call, step value 1, and we can just go to 1,000, and we'll do that. And then our time is going to be equal to our time step times our counter. So next we'll make a column for all of our heights. That of course starts with the initial height. And we'll also make our change in height. All right. So now this is the second equation we derived. For the second, it's the other equation we derived. So we have our flow going in minus our flow going out. Times our height here. Period for that 2 and 9. And this is all divided by our cross-sectional area. And now our change in height, of course, is going to be our new height is going to be our old height plus our change in height times our time step. And what we can do is we can double click on the bottom right corner of these, and if we insert a chart, we can see that we have our initial height of about 0.127, and then it goes up to about 0.028, and increases fast and then kind of slows down, eventually seeming to stop at about 0.028. And now I'm going to go to Python. For this, I want to import NumPy and NP. And from scipy.integrate, import solve IVP, our initial value problem. And then from plotly.subplots, import a subplot. All right. Now we can put in our initial variables. So Q and naught is again 0.1. Flow after the time starts is 0.15. Our cross-sectional area is 1 meter squared, and our cross-sectional area going out is 0.2 meters squared. Gravity is 9.81 meters per second squared, and now we can set our initial height. So these are all using, or these are both using the same equations. Flow going in over our cross-sectional area going out times our square root of 2 times g. And all of this is squared. And then we can define our function. So define BHDT, an initial time and height, across a time span with an initial height. And we just want to return our height at each time step. So that'll be our flow going in minus our flow going out. That's square root of 2 times g times h. And we will divide all of this by our cross-sectional area. And so that'll give a change in height each time. And next, we'll want to solve the initial value problem. BHDT. We need a end time. So right now, I'll just set that as 10 seconds there. So from 0 to t end, we want our h naught. And I want the method to be RADIO and dense output equal. That'll allow us to. So let's solver successfully reached the end of the integration interval. So now we'll be able to solve it, or to graph it. First thing I want to do is t-plot. So we'll just do a lens space here. So np.lenspace from 0 to the end, the 101 steps. I will make this, I will set a variable for this solve IVP function, and then we can do hplot equals res our result dot solve, just SOL. It'll be against tplot. Next, we have we want to make a figure, so sig equals make subplots, and then figure dot add scatter, where x equals time plot and y equals h plot. All right, and so here we have our graph, and you can see it pretty much looks the exact same as the Excel file. It should. It's all of the same equations there. We have our height starting at 0.127, 0.0127, increasing to about 0.0286 in that range. So now I'll actually be moving on, and this second part of the homework is having 3 tanks. Sorry, that's 3 tanks. And we can use all of these same initial values, and because we are at steady state, each of the 3 tanks will have the same starting height. So this h naught will just stay the same. Now I want to define a new function we'll call it DHCT3, time and a vector as the inputs. And that vector will give us H2, H1, H2, and H3. And then what we will return is a vector of all of our heights. So what I'm going to do is I'm going to steal this equation here real quick. So for this, I'm actually going to, when I return these, I'm just going to do Q in minus Q out, or sorry, Q1 out. And we'll of course divide those by the cross-sectional area. And then I'm going to take this. And for the next one, the flow coming out of the first tank is going to be this flow coming into the second tank. Do that, and then I will copy and paste again with Q2 out and Q3 out. Now what I want to do is define our flows coming out of each tank. Q1 out, Q2 out, and Q3 out are our three flows. And we'll just use this same expression, but with H1, H2, and H3. Right. So now that'll give 3 tanks over time. And we can do this same function here. I meant to copy that so that it goes a little faster. And so we'll want DHCT3 for, and our height, our initial heights will all be the same. And then we will go ahead and steal some more functions, some more equations. So we have H1 plot, H2 plot, and H3 plot for this. We no longer want to specify just that first row because we have 3 parts, 3 variables, and then we can just make another figure. So figure 2, and it'll be H1 plot, H2 plot, and H3 plot. Expected 3 got 1. Oh. I need to change this to result 3. Alright. So now we have these 3 tanks, and it's just the second one lags slightly behind the first, and the third lags slightly behind the second. But now what we're going to do is we're going to add a controller. So I want this to control off of the third tank's height. And my goal is going to be to increase the third tank's height by 20%. So our height set point is going to be 1.2 times our initial height. And then what we can do is set an error variable. So that'll just be our set point minus our third tank's height. And then we will have our flow adjust according to this error variable multiplied by some controller, AC. And just as a set point, I'm just going to say that's 5 to start off. We'll see how that goes. Okay, so now the graph looks a lot different, right? You have our first tank, a very large flow increase, and then that follows in the next 2. But as green increases, that error decreases, so the flow decreases as well. So that's what causes this oscillation. Uh, when when the third tank height increases, the first tank's flow into it decreases. And then once that flow decreases, that will lead to flow into the second and into the third reactor also decreasing, which means that the third tank will have its height decrease. So the error will increase and it goes back and forth. But what we can do is we can adjust this controller controller value here. So we just said it's 10 now. It oscillates more. Now, if we were really high, like the 50, it just doesn't work, right? I think that's with the value eventually hits 0, or it goes below 0, and yeah, the square root breaks. But if we find a good spot, 25 maybe, that still decreases. Went up to 30. Okay, so you can see now you can see these oscillations slightly increasing each time. We'll go to 29. All right, and yeah, so here the oscillations just seem to be the same every time. It doesn't seem to be increasing or decreasing at all. So with this controller setup, you just get this back and forth all the way. But what's interesting is actually checking if this is the set point we want. So our set point is 0.015, and this green, yeah, it just oscillates around that point, which makes sense. I think if we went back down to 5, so I think I saw, yeah, it doesn't reach it here. So at some point, 0.0142, which is, 0.001 lower than our set point, it goes to steady state, and this controller isn't able to account for that. As you see here, set point 0.015, it's also it's oscillating right in that value. So yeah, that'll be all for this homework. We'll be looking more into controllers in the future.